Okay, good afternoon, everyone. Thanks for this kind introduction. So today I'm going to present our preliminary results on the microfluidic surface-enhanced Raman sensors. And that's the work which we developed together with other colleagues. Karolina, who is not here, she's actually on maternity, she's an SIRS expert. And Firehun has worked on data analysis, and I helped with the setup of microfluidic experiment. So I've divided my talk into a few parts. I will first say a few words about SINTEF in case you don't know who we are. And then I say a few words about our motivation and also the background, and then show a few examples of the sensor substrates that we've developed and show measurement results with thiabendazole, which is a common pesticide, and Rhodamine. So SINTEF is one of the largest Europe's independent research organizations, and our mission is technology for a better society. SINTEF Digital is located in the south of Norway, and in the core of our department is our manufacturing facilities. We are the only independent complete silicon fabrication line in Norway. We run batch processing on 6-inch wafers and run really different types of projects from feasibility studies to production in 5 research areas: radiation sensors, classic MEMS, biomems, micro-optics, and piezo MEMS. This work is a collaboration between micro-optics group and biomems group. So the project, here is kind of the schematic view of the project, aims to develop portable sensing platforms for quick and reliable detection of environmental pollutants in surface waters, for example, by combining optical spectroscopy and microfluidics. And in some cases, we also looked into combining SIRS with electrochemistry. So the important part is nanostructured plasmonic chip, combining the advantages of highly specific and sensitive surface-enhanced Raman spectroscopy. And we've also looked into integrating these structures into a microfluidic channel for applying a laminar flow. Compared to well-established methods such as HPLC or GC, SIRS can avoid complicated and time-consuming sample prep and allowing real-time detection. So as everyone knows, environmental contamination with pesticides has multiple negative impacts on entire ecosystem, so it's really important project for us in this sense. Raman spectroscopy is an analytical technology characterized by inelastic scattering that occurs when light interacts with molecular vibrations. So there are 2 types of scattering, as you know: relay scattering, which is not so informative, and Raman scattering, which is highly informative about the chemical makeup. So SIRS is a nanoscale phenomenon which enhances the Raman signal of molecules absorbed in proximity of the metal nanostructured substrates. So the common way is to work with nanoparticles, or as will be shown in this work, we work with nanopatterns. So we are sort of in between these 2 cases because we use thin metal layer, but also nanostructured surfaces. SIRS metallic substrates can be classified into these 3 basic categories. So on the first is the colloidal nanoparticles assembled or immobilized on the solid substrates by bottom-up approach. Second is the colloidal nanoparticles in suspension, so different types of polymer-coated shells and so on. And third, nanostructures which are fabricated directly on solid substrate by lithography, for example, electron beam or focused ion beam. So the substrates from these 3 categories, they exhibit significant differences with respect to how homogeneous you can get them, and also geometries and different aspects of know-how of making them and complexity to be scaled up. So it's important actually to keep in mind that at the moment there are several commercial solutions which are available, but the challenges that are often pointed that if you want to take SIRS sort of out of the lab is the homogeneity and reproducibility of the SIRS signal, which is always or almost always related to variation in colloidal particles which agglomerate. And then it's kind of difficult to control what you are exactly measuring. So on the far left, you also see an example, a good reference, where they've compared 6 substrates, and they found that the relative standard deviation can range even up to 60%, depending on the type of substrate you use and your experiment. So the point of showing this is to say that the main drawback is poor reproducibility, and you need technologies that will help you to make robust substrates. This slide shows some of the previous work that we had on SIRS and DC SIRS. So we've tried different types of sensors based on roughening of commercial SPs, based on colloidal lithography, and also microfabricated patterned SIRS, either based on silicon nanostructures, which were metallized, or NIL resist, which was metallized. And in this work, I will talk about the SIRS substrates based on their metallized resist. So Nanoimprint lithography, that's a kind of simple introduction to it, compared to other common lithography techniques, although characterized by lower throughput. It allows for critical dimensions in sub-micron region, so it's interesting technology for us for many micro-optics components. Here is shown a very short schematic of the UV-NIL process used in this work. So first we start by fabricating the NIL stamp. We actually outsourced the fabrication of a master. It's the most expensive part of this process, otherwise it's very low cost. So the master can be made, for example, by combination of ABL and liftoff. Next, we proceed to soft stamp, which is fabricated and transferred on a plastic carrier using roll-on method, and then also UV cured. And afterwards, we proceed with the UV-NIL resist patterning itself. The silicon wafer, you start with a silicon wafer, which is primed and spin coated with the resist, ending up with a resist thickness of about 170 nanometers. Finally, a roll-on imprinting was performed and UV exposed. As the last step, the fabricated nanostructures were coated with thin gold film. So in short, UV-NIL is a great technique, but there are often pros and cons that people point. In terms of pros, excellent resolution. As mentioned, high throughput, you can work with large area patterning, and it's low cost. So it's a really strong candidate for high volume production, and also 3D structures are feasible. As cons, people often work about, so it's a tedious optimization that is required. One of the issues is, for example, residual layer and adhesion and presence of the particles that may interfere with the pattern. Here, I show the design that we've used. It's actually a design developed by my colleague, and the reference you see there. So if you want the details, you can read it in the paper. But it's an array of C-shaped nanostructures. The shape and size of the nanostructure pattern was designed to obtain plasma resonance between 700 and 900 nanometer wavelength range, with intention to create multiple hotspots in the electrical field and take fabrication limitations into account. So while lateral dimensions in these models were fixed because we used a master fabricated by ABL, the plasma resonances could be modified by varying the deposited gold thicknesses. So here you see the examples of their fabricated nanostructured substrates. These are high-resolution SEM images of both top and cross-sectional. And you see, so it's reproducible and nice process for this design. It's not all designs that come out equally efficient. So at this stage, when we fabricated the SIRS substrates and it metallized, in principle, we could stop, and substrates could be characterized by further by manual deposition of 1-2 microliter droplets on the surface and drying, and that's how analysis is still done in majority of works dedicated to SIRS. However, in this case, in addition to possible variability between the SIRS substrates, you also add an error by manual handling of your sample. So in this work, we integrated our SIRS substrates in a microfluidic channel. It's a simple assembly that we've used Our channels are about 180 microns high. We use double-side adhesive, which was pre-cut. And the total volume of the channels, so on the chambers that we've used, is usually around 0.5 microliter, 1 microliter. So of course, it's possible to go more complex with the bonding technologies, but this straightforward way of assembling our sensors just helped us to screen different versions and establish proof of concept. But we also, for example, have a BCB bonding technology that could be used within the clean room, or it's possible to pattern the electrodes. So the results that I show here are on substrates which were fully metallized without patterning of the electrodes. For SERS measurements, we used a portable Raman spectrometer. It's not really small, maybe about, I don't know, 0.5 meter, 20 centimeters, but it's still portable. It was equipped with a CCD array detector and 785 excitation wavelength fiber optic probe. And yeah, we used native software from this equipment for analysis. We use a 20% laser power and 10 seconds acquisition. So for the fluidic experiments, we had a syringe pump, which could be programmable, and the flow rates that we've set up are between 12.5 and 50 microliters per minute. So we were still in laminar flow regime for all our experiments. And I've shown the example of the measurements with thiabendazole. It's a common fungicide which is used in agricultural fields, and Rhodamine. So interestingly, actually, it was quite hard for us to find the chemical which interacted well enough with the metallic substrate so that we could measure it. And thiabendazole was not the first heat with which we started. So this figure shows Raman intensity for different concentrations of thiabendazole, as well as on the right side dependence at one of the characteristic peaks. So as you see, we could detect in static conditions TBZ down to 10⁻⁷ molar. And it's already quite good results because we know from food analysis experts, for example, that pesticides need to be if you're able to detect pesticides already at 10⁻⁵, 10⁻⁶, then it's already a relevant range. So now to some of the flow experiments, we plotted the results dependent on the flow rate of 12.5, 25, and 50. And as you can see, it's evident that there is a progressive increase in Raman intensity corresponding to the Rhodamine peaks observed. And additionally, the flow rate demonstrates a notable impact on the rate of the pre-concentration. So a low flow rate corresponds to a slower pre-concentration effect. Another interesting effect, just briefly, it really matters if your substance is in water or in ethanol. So for example, TBZ, we were not able to pre-concentrate it in ethanol. So one of the possible explanations we thought could be, of course, poor compatibility of the NIL resist with ethanol, but actually we were able to detect other compounds in ethanol in it. Another possibility is inability to pre-concentrate TBZ due to poor interaction of the analyte itself with the source substrate, so it's more likely. This is also another example where we try to remove Rhodamine after application. So it's actually promising to use microfluidics also for cleanup of the substrates. So it's really important if you want to take the sensors in the field that you can introduce a protocol that you wash them away and then measure again. So I see that I have to hurry up. So basically, these were our preliminary results, and we think that UV-NIL based Nanoimprint metallized is an interesting concept for doing quick analysis, and also kind of we plan to take it further to the field, and actually recently got one project based on similar technology as well. So continue working on that. Thanks for your attention.